This presentation is dedicated to the systematic exploration of urban resilience strategies specifically localized at the neighborhood scale. In the contemporary epoch of the Anthropocene, urban environments are increasingly characterized by their exposure to nonlinear risks, ranging from acute meteorological shocks to chronic socio-economic stressors. It is argued that traditional disaster management paradigms, which prioritize rigid resistance, are no longer sufficient. Consequently, a multidimensional socio-technical framework is proposed. Within this framework, the integration of physical attributes, such as walkability, mixed use, and thermal zoning, with systemic strategies like decentralization and integrated green infrastructure is examined. The fundamental objective of this presentation is to outline how the neighborhood unit serves as the essential building block for fostering a resilient urban future through the synthesis of spatial morphology and social agency. Urban resilience is built upon a multifaceted framework that begins with a robust theoretical understanding of the concept of resilience and the strategic mesoscale advantage of the neighborhood unit. By viewing neighborhoods as complex adaptive systems, practitioners can implement the principle of decentralization and optimize street network topology to ensure structural robustness. Within this spatial fabric, walkability serves as a primary resilience strategy and a critical survival mechanism, while the emergent neighborhood model and mixed-use development foster functional redundancy and social cohesion. Environmental stability is further enhanced through thermal zoning, climate sensitivity measures, and the pursuit of passive survivability. These physical attributes are integrated with nature-based solutions like integrated green infrastructure and technical systems such as decentralized energy production to create resource autonomy. Finally, this technical hardware is activated by the social hardware of community hubs and supported by transformational governance and tactical urbanism, leading to a comprehensive synthesis of actionable takeaways and conclusions for a resilient urban future. For resilience to be effectively operationalized, it must be defined with academic precision. Within the seminal framework which poses the normative questions, resilience for whom, what, when, where, and why, it is recognized that resilience is not a value-neutral technical objective but is deeply rooted in political and social contexts. A system is not considered truly resilient if its physical robustness is achieved at the expense of social equity. Therefore, a balance must be struck between robustness, the physical durability of the built environment, and resourcefulness, the capacity of a community to mobilize assets under pressure. Resilience is viewed as an iterative process of constant learning, where every disruption serves as a feedback loop to refine subsequent urban configurations. The ultimate goal is the cultivation of a capacity to adapt and transform amidst pervasive uncertainty. The neighborhood can be identified as the critical mesoscale of urban intervention. It is observed that macro-level citywide strategies often suffer from abstraction and fail to address localized microclimates or specific socio-economic requirements. Conversely, building-scale interventions are often too fragmented to ensure systemic stability. The neighborhood scale is identified as the optimal level for the integration of technical systems, such as microgrids or localized water management, while simultaneously fostering social cohesion. At this scale, urban form, including parameters like building heights, street widths, and the distribution of open spaces, is seen to directly dictate the daily operational capacity and survival potential of the inhabitants. By decentralizing resilience strategies to the neighborhood level, a modular urban fabric is created, which is inherently more robust than a system reliant on a singular, centralized core. Neighborhoods are conceptualized as complex adaptive systems, wherein transportation networks, energy grids, and social structures are deeply interdependent. It is understood that a modification in one subsystem inevitably impacts the others. Within this adaptive framework, urban systems are observed to progress through continuous cycles of growth, conservation, release, and reorganization. Resilience planning is based on the acceptance that release, or shock, is an inherent part of the system cycle. Instead of futile attempts at total prevention, neighborhoods are designed to facilitate rapid reorganization. By analyzing the feedback loops between mixed-use development and integrated green infrastructure, it is ensured that when one system reaches a critical threshold, auxiliary systems provide the necessary support to maintain overall functionality. Centralization is identified as a primary vulnerability in modern urban configurations. Dependence on distant, singular power plants or massive water mains creates a high risk of cascading failures. Decentralization is advocated as a strategic defense mechanism. By decomposing the urban environment into semi-autonomous neighborhood modules, the propagation of disruptions is effectively contained. The objective for a resilient neighborhood is the attainment of resource autonomy. This is achieved through the implementation of decentralized energy production and localized water and waste management. While the neighborhood remains connected to the macro city, it is equipped with islanding capacity, allowing for independent operation during macro grid failures. This modularity is presented as a fundamental requirement for systemic robustness in the face of contemporary environmental and technical threats. The street network is viewed as the structural backbone of the neighborhood. The topology, or geometric arrangement of this network is a primary determinant of its robustness. Here, a comparison is made between highly connected grid networks and hierarchical, tree-like structures. The grid is characterized by inherent redundancy, providing multiple alternative paths for movement if primary intersections are compromised. In contrast, hierarchical models are seen to be susceptible to isolation if a singular arterial road is blocked. By utilizing computational tools such as OSMNX, a Python library that allows users to download, model, analyze, and visualize street networks and other geospatial data from OpenStreetMap, these connectivity patterns are quantified. It is argued that a resilient neighborhood must prioritize a porous, fine-grained street network, ensuring the continuous flow of residents and essential resources even when primary transportation routes are obstructed. Therefore, in terms of resilience, complete grids or matching pairs prioritize high connectivity and redundancy to ensure system stability. In contrast, the least resilient patterns, like ring networks or diverging tails, are more vulnerable to disruption due to their lack of alternative paths. While walkability is frequently discussed in terms of public health or environmental sustainability, it is analyzed here as a critical survival mechanism and a primary redundant transport mode. In scenarios involving fuel shortages, cyber attacks on automated transit, or structural damage to road surfaces, the capacity for pedestrian movement determines the continuous accessibility of life-sustaining services. Walkability is no longer a luxury but a fundamental necessity for the resilient city, providing a fail-safe mobility option when high-tech infrastructure collapses. A resilient neighborhood is one where essential resources and community hubs are situated within a 5 to 15-minute walking radius. This requires high intersection density and the provision of shaded, safe pedestrian corridors, a structural requirement that can be rigorously quantified through computational tools such as OSMNX to ensure a porous and fine-grained network topology. Furthermore, the geometric configuration of walkable urban forms reduces the neighborhood's sensitivity to external transportation shocks. By decoupling survival needs from motorized transit through a robust pedestrian-oriented morphology, the neighborhood achieves a higher degree of self-sufficiency and functional continuity during the initial stages of a crisis. The spatial formation of walkable networks is fundamentally defined through the emergent neighborhood model, described as a departure from static, administrative zoning toward a dynamic, living system approach. This model posits that neighborhoods are not merely administrative constructs but emerge from the underlying geometry of street networks. It is suggested that when street networks are designed with high, between-us centrality, social and commercial centers are naturally fostered at the most connected nodes. This spontaneous order is regarded as more resilient than rigid, top-down master planning because it aligns physical form with actual human behavior and the human measure of urban life. The model shares a lineage with the traditional neighborhood unit, particularly in the emphasis on pedestrian safety and the creation of sanctuary areas protected from heavy-through traffic. However, where the historical model was criticized for being an isolated, inward-looking cell with clear boundaries, the emergent neighborhood model proposes a more permeable and overlapping structure. It emphasizes a chronocentric vision, like the 15-minute city, where time becomes a climate agent and a tool for regenerative urban science. While the neighborhood unit utilized the elementary school as the fixed focal point, the emergent model argues that urban nuclei should be mobile and multi-scale, emerging naturally where connectivity and service presence are highest. Similarly, the model aligns with transit-oriented development, TOD, by prioritizing walkability and ecological community structures. However, the emergent neighborhood model seeks to evolve beyond the TOD paradigm, which can present health risks due to high-volume concentration. Instead of just maximizing density, it focuses on optimizing network capacity and territorial displacements. It functions as a local entity, combining local place identity with access to the global world through mobility and digital infrastructures. It suggests that if the geometry and digital upgrading are correct, functional diversity and social capital will follow as a natural byproduct. Ultimately, by adhering to these geometric laws of connectivity and integrating micromobility solutions, a spatial order is created that reinforces the neighborhood's capacity for self-organization during disturbances. Unlike rigid mid-20th century planning, this approach fosters a resilient urban fabric that can adapt to socio-economic shifts and unforeseen events. By incorporating zero-minute trips through digital accessibility and remote working flexibility, the neighborhood remains a dynamic, sustainable, and inclusive participant in the life of the city rather than a static artifact. Mixed-use development is presented as the primary driver of functional diversity within the urban fabric. Purely residential zones are characterized as dormitories of vulnerability, lacking the localized resources necessary for crisis management. Conversely, mixed-use neighborhoods, integrating residential, commercial, and light industrial functions, possess functional redundancy. Local commercial spaces are identified as potential distribution points, and office environments are seen as adaptable for emergency use. This diversity ensures that the 15-minute city concept functions as a robust safety net. By localizing the economy and essential services, the circuity of movement is decreased, and the resourcefulness of the community is increased. The synergy between functional variety and spatial form is seen to significantly bolster the neighborhood's adaptive capacity. The escalation of global temperatures necessitates that neighborhoods be designed to mitigate the urban heat island effect. This is addressed through the application of thermal zoning. Thermal zoning involves the strategic manipulation of urban morphology to influence the local microclimate. Through the variation of building heights to facilitate mutual shading, and the alignment of streets to serve as ventilation corridors, ambient temperatures are effectively lowered. The trade-offs between urban density and thermal comfort are visualized on this slide. It is maintained that a resilient neighborhood manages its climate sensitivity by ensuring that cool refuges are accessible even in dense urban cores. This approach is identified as a critical intervention for the prevention of heat-related mortality during extreme meteorological events. The concept of passive survivability is identified as a vital component of thermal resilience. It is defined as the capacity of the built environment to maintain habitable conditions, specifically safe internal temperatures and air quality, during extended disruptions to the electrical grid. In a resilient neighborhood, reliance on mechanical air conditioning is minimized through the use of porous morphology. This involves the design of buildings and urban blocks that facilitate natural cross-ventilation and utilize thermal mass for temperature regulation. Fine-grained urban forms are often superior in this regard compared to massive, coarse-grained superblocks. Passive survivability is presented as a life-saving feature, particularly for vulnerable populations, ensuring that the neighborhood remains a safe environment even when active technical systems are incapacitated. The green hardware of the neighborhood is explored through integrated green infrastructure. It is observed that traditional gray infrastructure is often characterized by brittle failure when its fixed capacity is exceeded. IGI, comprising bioswales, rain gardens, and permeable pavements, follows a safe-to-fail logic. Stormwater is managed at the source through localized absorption, thereby reducing the hydraulic pressure on municipal sewers and mitigating flood risks. Furthermore, IGI is seen to provide ecological redundancy by contributing to local cooling and air purification. By integrating these nature-based solutions into the existing street network, a sponge neighborhood is created, utilizing ecosystem services to buffer the community against environmental shocks and enhancing the overall microclimatic stability. The traditional dependence of modern neighborhoods on a centralized electricity grid is increasingly identified as a significant systemic vulnerability, particularly in the face of climate-induced disruptions and infrastructure aging. To mitigate these risks, decentralized energy systems, which incorporate neighborhood-scale renewable generation and localized storage, are proposed to transform the passive residential cluster into an active prosumer. By generating and managing their own power, these mesoscale units transition from being mere consumers to integral components of a distributed energy architecture. A primary technical advantage of this transition is the islanding capability of microgrids. This capability allows a neighborhood to disconnect from the macrogrid to maintain critical local power during wider outages. In the event of a macrogrid failure, The neighborhood microgrid is capable of independent operation, ensuring the continued functionality of essential services, such as community hubs, water pumping stations, and medical facilities. Such resource autonomy, supported by neighborhood solar arrays, wind, and microgrids, is seen as critical for systemic robustness. Beyond technical reliability, the transition encompasses vital social dimensions and promotes equity. Community-led energy cooperatives have been found to reduce energy poverty by democratizing access to low-cost renewables and fostering localized economic strength. By keeping energy expenditures within the community and creating local green jobs, these systems contribute to the long-term socio-economic resilience of the mesoscale. This shift essentially redefines energy as a common good, where local governance of resources leads to a more sustainable, equitable, and disaster-resilient urban fabric. While technical infrastructure is essential, it is maintained that social capital is the primary driver of recovery. Community hubs, including urban amenities such as libraries, plazas, and schools, are conceptualized as the social hardware of resilience. These spaces are where bonding and bridging social networks are cultivated. During disturbances, these hubs are activated as centers for information exchange and mutual aid. Communities characterized by high levels of trust and social cohesion exhibit significantly faster recovery rates. The design of a resilient neighborhood must ensure that these hubs are physically robust, equipped with decentralized energy backups, and situated at the most accessible, walkable nodes within the street network to ensure their utility for the entire population during crises. The management of complex, decentralized urban systems is argued to require transformational governance. It is observed that traditional, top-down planning models are often too rigid for the dynamic nature of urban resilience. Instead, an adaptive, bottom-up approach is advocated, characterized by learning by doing. The utilization of situated knowledge, the localized expertise of residents, is emphasized to identify vulnerabilities that may be overlooked by macro-scale analysis. Resilient governance is defined by its inclusivity, ensuring that residents are active participants in the management of their integrated green infrastructure and decentralized energy systems. By fostering collective ownership and agency, it is ensured that resilience strategies are both technically robust and socially sustainable, thereby strengthening the neighborhood's long-term adaptive capacity. Tactical urbanism is presented as a primary mechanism for the implementation of adaptive governance. These are defined as low-cost, temporary physical interventions, such as pop-up parks or temporary pedestrian zones, that facilitate the real-time testing of resilience strategies. By utilizing these methods, the performance of specific urban configurations, such as cooling corridors, can be measured before permanent structural investments are made. This process creates a feedback loop that allows the neighborhood to evolve incrementally and adaptively. It is maintained that tactical urbanism reduces the risk of costly, permanent errors and empowers the community to participate directly in the morphological evolution of their environment. This agility is identified as a necessary trait for any complex adaptive system seeking to maintain resilience. The following synthesis serves as the comprehensive summary and actionable takeaways for the entire presentation, integrating structural strategies with socio-technical adaptive mechanisms. The transition toward urban resilience in the Anthropocene necessitates a shift from rigid resistance to a multidimensional, socio-technical framework centered at the neighborhood mesoscale. By conceptualizing neighborhoods as complex adaptive systems, we can implement decentralization to achieve resource autonomy and islanding capacity, effectively decomposing the urban fabric into semi-autonomous modules that contain cascading failures. The structural robustness of these modules is dictated by their street network topology, where high connectivity grid patterns provide the necessary redundancy to maintain resource flow during disruptions. This spatial order is best realized through the emergent neighborhood model, which leverages between-us centrality to foster spontaneous social and commercial centers, moving away from the isolated cells of traditional planning toward a more permeable, living system. Within this fabric, walkability and mixed-use development function as primary survival mechanisms, ensuring functional redundancy and accessibility to life-sustaining services within a pedestrian radius when high-tech infrastructure fails. Environmental stability is further reinforced through thermal zoning and passive survivability, which utilize urban morphology to maintain habitable conditions, and integrated green infrastructure, IGI, which adopts a safe-to-fail logic to manage meteorological shocks. Ultimately, this physical hardware is activated by the social hardware of community hubs and social capital, all governed through an adaptive, transformational approach that utilizes tactical urbanism as a feedback loop to refine subsequent urban configurations amidst pervasive uncertainty. In conclusion, urban resilience is conceptualized not as a fixed destination, but as an ongoing process of adaptation and transformation. The neighborhood is reaffirmed as the most critical scale for urban survival in the 21st century. Through the integration of the physical, hardware, of street networks and decentralized energy with the social, software, of community hubs and inclusive governance, a truly resilient urban fabric is cultivated. It is advocated that practitioners move away from the rigidities of 20th century planning and embrace the modular, decentralized, and emergent qualities of the mesoscale. By empowering the neighborhood, a future is built that is capable of withstanding the shocks of the present and navigating the uncertainties of the future.